Welcome everybody to our today's seminar. We are glad to have with us Dr. Moise Bonilla-Licea from Mexico. As you already see on the screen, the talk is about quantum computers, quantum gates in quantum computers. The local expert here for us is Thanasis Zemos. He will do a short introduction of the speaker and then we can follow. So Moses, Thanasis will introduce you now.
So, hello everybody. From me, here today we are very glad to have Dr. Moise Bonilla-Licea, a postdoctoral student researcher in the Center for Research and Advanced Studies of the National Polytechnical Institute of Mexico. Moise has received the degree in his bachelor degree in physical engineering from the Universidad Iberoamericana in Mexico in 2014. Then he attended for the master's degree from the Center for Research and Advanced Studies in 2017, and then he earned his PhD from the Goethe University of Frankfurt, Germany, in 2021. He has conducted postdoctoral research he has been conducting postdoctoral research from 2022 up to 2024 with the Department of Automatic Control of the above center, focusing on the application of classical modern control theory in quantum control. He has published several papers in journals like Physics Letters A and Foundations of Physics, as well as in engineering journals such as IEEE Transactions on Automatic Control. And his research interests include the formulation of Mandelung's quantum mechanics, quantum control, and the pedagogy of quantum mechanics. So, Moise, we are ready to hear you. If you don't have any questions, we can start.
Okay. Well, first of all, I would like to thank you, Dr. Zemos, for the invitation. And in this occasion, I will be talking, well, the talk is titled A Simple Design of Quantum Gates in Quantum Computers. So there are two parts. On one hand, we have quantum computing, and on the other hand, we will apply some formalism to design quantum gates. So first, we need to understand what is quantum computing. And to understand briefly what is quantum computer, first, we need to understand what is a classical bit, just a classical one. So imagine you have two electrical wires, and then you start measuring the voltage between these two electrical wires. And arbitrarily, you will choose to assign a computational state 0 if the voltage between the wires is 0, and you will assign a state 1 every time you measure 5 volts between these wires, let's say. So that's basically a classical bit. It's a physical system in which you have assigned two states depending on the voltage. And something very important about the classical bit is that it has the property of having a well-defined state for every time. So if at any time I measure the voltage, I will always be able to assign either 0, either 1, either 0, either 1. There is no undetermination. Now, when we go to the quantum world, we face a situation. In quantum systems, we have the situation that the systems are undetermined. And this is briefly summarized in the Copenhagen interpretation, which I will read a quote from Niels Bohr, which is the founder of this interpretation upon which is based the quantum theory. Basically, he says, the entire formalism is to be considered as a tool for deriving predictions of definite or statistical character as regards information obtainable under experimental conditions described in classical terms, only to be regarded as expressing the probability for the occurrence of individual events observable under well-defined experimental conditions. So basically, it says that what we know about the quantum systems is always of statistical character. And this statistical character comes from the information about the experimental preparation of a quantum system. That's on one hand. On the other hand, we already know that in quantum physics, there are systems that have only two energy levels. Think about spin, for example. So you have systems with energy E0 and E1. And according to the previous interpretation that I quoted, basically individual events are unpredictable. If I measure the energy of these two-level systems, I will never, in general, I'm not able to say what will be the outcome of the measurement, which is opposite to the classical bit. For example, if I take a classical bit and I measure the voltage, I will either have 0 volts, 5 volts. There is no indeterminacy. But with if we take a quantum system with two energy levels, and I measure the energy, there is no basically there is no determined energy. Sometimes I will have E0, sometimes I will have E1. But remember the interpretation of Bohr. Basically, he says that the only information that we can extract from quantum systems is the statistical patterns. That means that I won't be able to know for sure if the outcome of the measurement is E0 or E1, but what I will know is the probability of occurrence. So I will know, for instance, in this case, that 40% of the times I will get E0 and 60% of the times I will have E1. And that's what we can access, the information that we can extract from the quantum systems. So in this case, the two-level systems is the prototype for the quantum bit, so to say. Why? Because we have the same structure. We have two states. In this case, one state has energy E0, the other state has energy E1. And we have an assignation from, for instance, if we measure energy E0, we will assign the computation, the bit 0. And if we have the energy E1, then we will assign the bit 1. So we have the same structure, but the main difference between the classical bit and the quantum bit is that in general, the state is undetermined all the time. So we never have the certainty of what is the outcome of the measurement, just the probabilities. And this is important because in a classical bit, what you manipulate is the voltage. So you manipulate the 0 and the 1. You turn 1 into 0 or 0 into 1. But in quantum computing, what you manipulate are the probabilities. That's what we will manipulate, the probabilities of 0 and the probability of 1. Now, what is, we can wonder, what is the advantage of using quantum systems for computational interest? The first advantage is the following. Take, for instance, classical computing. Classical computing is based on classical logic, which is irreversible logic. Why is it irreversible? Take, for instance, the logic gate AND. If I know that the output is 0, I have no way to deduce if I have 0, 0, 0, 1, or 1, 0. So that means that it's irreversible because I cannot predict the income from the outcome. And this has a physical consequence. Since there is a loss of information, then there is an increase of entropy. And the increase of entropy is translated into heat. So just by using irreversible logic, all classical computational systems will generate heat. On the contrary, in the quantum, for the quantum systems, the logic is reversible. Why is it reversible? Because all the quantum systems are acted upon unitary transformations. And the important part of unitary transformations is that they are invertible matrices. So every time we operate over a quantum system, we apply an invertible matrix. And if you apply an invertible matrix, that means that if I know the outcome, I can use the inverse of the matrix, and then I can predict what was the income, okay? The income. So basically, the input, sorry. So if I know the output, I know I can deduce what is the input. And then there is no loss of information. And then if there is no loss of information, there is no increase of entropy, and therefore there is no dissipated heat. That's one of the advantages. The second advantage is that basically in a classical computer, when you perform a search in a database, in an unstructured database, and for example, you want to find this register, this binary register 10111, you basically, in a nutshell, what you do is checking register by register. So you have a list, and then you start checking every item of the list. And then there are strategies, but basically that's what you do. You check item by item. But in a quantum computer, as I mentioned before, what is manipulated is the probability. The probability of occurrence of the items, of the registers. So since you manipulate the probability, as we will see later in the talk, basically you can manipulate that the probability of occurrence can have a peak in the item of interest. So this is somehow a way of performing parallel computing, so to say. So one of the advantages is that while here you check item by item, here we check every item, all the items, manipulating all the probabilities, okay? And that's one of the advantages because it speeds up the finding of a given item in a database. So that's basically quantum computing in a nutshell. Now, let's understand the qubits, the concept of qubit in a simple way. So in 3 steps, in the first step, we have a physical system. It can be superconducting circuits or nuclei from molecules. It really doesn't matter. There is just a physical system which has 2 energies, E0 and E1. And then according to quantum mechanics, you can describe the experimental preparation or the quantum state in a sphere, in a 3D system, and every point on this sphere, which is called the block sphere, will be directly related to a specific preparation of the quantum bit of the quantum system, okay? Which will deliver the associated probabilities. Now, this sphere, which looks maybe complicated, is nothing more than a probability ruler. So basically, you can think this sphere as a ruler of probability, in which case, if your system is in this point, in the North Pole, then it means that 100% of the times, the system will have, the quantum bit will have 0. If you are at any point of this parallel circle, then it means that, or let's say there is 75% of probability that your quantum bit is 0, and 25% that it's 1, and so on. And for every point on the sphere, you have a percentage of probability. And of course, if you are in the South Pole, then it means that there are 0% probability that your quantum qubit is 0, and there is 100% probability that your quantum bit is 1. So this block sphere is just like a ruler of probabilities, basically. And then here comes the question: what is a quantum gate? In the classical case, a logic gate is basically manipulating the voltages to turn zeros to 1 or 1 to zeros under some conditions. But in the quantum case, the question is, what is a quantum gate? A quantum logical gate is basically you send electromagnetic radiation, it can be microwaves or RF, radio frequency, to your physical system. And then this interaction will cause that you will start in one point of the Bloch sphere, and then you will end up in another point of the Bloch sphere. Now, what does that mean? Remember what I told you. The Bloch sphere is nothing more than a probability ruler. So basically, the effect of the quantum gate means that you go, let's say, from 100% of the times the quantum bit is 0 to 75% the quantum bit is 0. So basically, a quantum gate, the function of a quantum gate is manipulating the probability of occurrence of the quantum bit. That's what the quantum gate does. And it does it through the application of electromagnetic radiation. Let's see one example. For instance, the quantum equivalent of the NOT gate. In the classical case, a NOT gate, it turns 0 into 1, 1 into 0. That's it. In the quantum case, it's more or less similar. In the quantum case, you will have 100% of the times, when you have 100% of the times the quantum bit 0, you apply the gate, and at the end, you will have 0% of the times 0 and 100% of the times 1. That's basically the quantum NOT gate, and vice versa. The other way around. If you have 100% of the times 1, then the quantum NOT gate will cause that at the end you will have 0% of the times the 1 and 100% of the times 0. And in this case, for instance, this is achieved by applying these electromagnetic pulses, basically staircase magnetic fields. We will talk about this a little bit later. And then basically with this, you can already guess what a quantum algorithm consists. It basically, a quantum algorithm is basically a recipe like reading music. There is electromagnetic fields, and every time you apply a quantum logic gate, then you apply some electromagnetic pulse that is characterized by amplitude, frequency, phase, envelope, and duration. And once you apply this sequence of pulses, then basically you are applying some quantum logical gates. That's it in a nutshell. And then we have to remember again the interpretation of the quantum theory. Everything has to do with statistical character. So in order to make sense about to the quantum algorithms, the output, we need to basically interpret probabilities. And remember that a probability, how to compute a probability? A probability is computed basically by dividing the number of trials where the event of interest is presented over the number of total trials. And then you have to do this for a large enough number of trials. And then when you do this ratio, basically the limit is a probability. So that means that when you perform the quantum algorithm, you have to repeat this algorithm a large enough number of times so that you can measure the probability. It's not enough just executing the algorithm once. You have to repeat it a large enough of times. Okay, so basically, that's an overview of what is quantum computing and what is the quantum qubit, the quantum bit, basically. Now, I will be talking about the Madelung picture to design these quantum gates for manipulating the quantum bits. And for this, we have to do a little bit of history. So we have to go back to 1926. Then there is Erwin Madelung, a German physicist, and he found that from the Schrödinger papers of 1925, so on, that he found basically that you can reformulate back then the formulation of Schrödinger into a hydrodynamical equations. And well, this idea then is retaken by de Broglie years later, and as we already know, in 1952 by David Von. But originally the idea was found by Madelung. That's why we call it the Madelung picture, so to say. And in this case, it's basically just a mathematical reformulation of the theory. Madelung never tried to impose or add additional postulates, contrary to David Bohm. So basically, the Madelung picture is just reformulating the formalism into hydrodynamic form. How does that look like? Basically like this. You take the wave function, which is the quantum state in position space. You express it in a polar form. So you have amplitude and phase. The amplitude is related to the probability density of the system. And that's it. No. So when you express in this form the wave function, basically the Schrödinger equation in position space is decoupled in two real partial differential equations. One is the well-known continuity equation, which suggests that this hydrodynamic future. And the other one is just a modified Hamilton-Jacobi equation, which is similar to the classical case, just with this additional term, which is the quantum contribution, right? And then there is two advantages of considering the Madelung picture, because so far in the conventional literature in the community, quantum computing has already 3-4 decades already, and it is treated by the conventional formalism of Dirac notation and so on, right? So the question arises, why do we even bother to apply Madelung picture to the quantum bit if there is already a well-established formalism for treating quantum bits? And the answer has basically one aspect. As I told you, the function of the quantum gates is basically manipulating the probabilities, right? And if you note here in the Madelung picture, the probability density itself is a variable of the equation. So that means that if we solve these equations, we already have the probability density, which is different from the conventional formulation, in which you have for instance, the quantum state, and then you have to project in order to extract the probability, right? So it's a little bit different. In this case, we directly manipulate the probability of the system. So basically, Madelung dynamical equations manipulate probabilities, and this is something interesting to explore for the quantum gates. If this directly manipulates the probabilities, then there must be something when you design these quantum gates, right? But there is a problem. We have to first remember, how does it look like, a quantum processor, a quantum bit? What's the how does it look like? So basically, in this slide, I'm showing you 5 common quantum processors. Basically, the most famous ones. One is the superconducting qubit, which is just aluminum and aluminum oxide in a superconducting state. And then in this case, the energy associated to these superconducting circuits is 2 energies, and then we have again the qubit. In the quantum dot, basically you have potential wells, and then you have electrons, and then if there's an electron, it's a 1. If there is not, there is a 0, etc. It's very similar to the behavior of transistors. Then you have color centers, which is, for instance, diamond with impurities of nitrogen, in which case you manipulate the spin of the nuclei of a given atom. You have also trapped ions, which you have, as the name suggests, you have ions that are trapped into a solid state system. And then with the help of lasers or electromagnetic radiation, you basically you cause that this ion will go into in a given transition of energies, and then in this way you manipulate the transitions between energy E0 and energy E1. Then you have the topological qubit, etc. No, but if you observe something that all these 5 quantum processors have in common is that they are motionless. They don't move. So they don't move when we apply the electromagnetic radiation. They don't move. And as we saw earlier, the Madelung picture, the hydrodynamical equations of the quantum systems involve either position space or momentum space. But this is not useful because our processors doesn't move. Okay, so if they don't move, then the question that arises naturally is it possible to exploit the Madelung picture outside those spaces? And the answer is yes. And the trick is the following. You have to remember that the quantum state, for instance, in the Bloch sphere, which is our prototype for the quantum bit, can be expressed in the well-known formula, which is the number 1. You have cosine theta half of the state 0 plus sine of theta half exponential of I phi of the state 1, right? But something that maybe not many people already saw is that this is already in polar form, right? Which is the starting point of the Madelung picture is expressing the quantum state in polar form. And here you already have the polar form. You have amplitude, phase, amplitude. Here the phase is 0. And again, the amplitude, the square of the module of these coefficients will give you the probability. So basically, if you know the angle theta, you already know the probability or the probability density, right? And here in this case, the phi is the phase. So there is kind of something similar situation from the starting point of Madelung picture. It's the same. So we will apply the same concepts of Madelung picture, but in the spin space, not in the position space. No, in the spin space. So in order to do that, let's do a small example. So basically, remember let's take, for instance, the operator spin Sx. And we already know from the quantum theory that if you apply Sx to the state 0, then you have h bar over 2 applied to the state 1. And similarly to if we apply Sx to the state 1, right? We have this is the effect of this operator. And then we have to remember the polar decomposition, right? The polar decomposition in the Bloch sphere is given by this. So if I applied Sx to this state, then we turn 0 into 1, 1 into 0, and there will be an h bar over 2 multiplying in both sides. And then since if you remember earlier, I said when I showed the hydrodynamical equations, that's basically we have to evaluate the function in every point of the space, right? Now in the spin state space, there are just 2 points, 0 and 1. So we have to evaluate the Sx in 0 and in 1, right? So in this case, we will project in 0. So basically, we will collect this term, which is this one. And then we will divide by the quantum state in 0. So from this one, and then we got the tangent, and this is what we call the Madelung quantity. We will see later how it looks like, right? So then we do the an analogous procedure, but evaluating in 1, and then we have this expression, right? So we have the effect of the observable Sx for state 0, which is given by this in the spin space. And then we have Sx applied to for the quantum state 1. And then we have this term, which is expressed in the quantum space. And then we can repeat this procedure for Sy and Sz, right? And we have these 6 complex quantities, which describe the effect of each one of these spin directions. And something very important is that from the Schrödinger equation, the Hamiltonian basically will always have this expression in the spin space for 0 and for 1, right? Here we already computed all the possible, all the interesting observables. We already computed their Madelung quantities, the Sx, Sy, Sz, and Hamiltonian for the value 0 and for the value 1. So we have, let's say, all the ingredients for the recipe. Now we have to express the Hamiltonian, right? So let's take, for instance, the following processor, which is the NMR, so nuclear magnetic resonance. It consists on a glass tube, for instance. For example, a glass tube filled with a sample in liquid state. And then there are molecules, and these molecules have atoms, which in turn have nuclei. And then in this NMR processor, we manipulate the magnetic moment of these nuclei, right? For instance, if we put water, basically we manipulate the nuclei of the hydrogen atoms. And this manipulation, we do this manipulation with basically a solenoid, which is a static magnetic field B0. And then we put RF coils to perform the quantum gate. We will see later how is this performed. So we have 2 magnetic fields, B0 in the Z direction and B1 in the, let's say, X direction. So for this magnetic system, we already know that the Hamiltonian is basically involves the spin observables and the associated magnetic fields, the magnetic field in X direction, the magnetic field in Y direction, the magnetic field in Z direction, where gamma is the gyromagnetic constant of the nuclei. So in this case, what we need to do is basically apply the quantum state, then project to 0 or 1, and then divide by the quantum state. And then we get this equation 6 can be translated into this Madelung quantity for the state 0 and this other Madelung quantity for the quantum state 1. And at this point, what we need to do is just substitute the Madelung quantities that we found previously. Now, I know that maybe there are, it seems like there are a lot of equations, but you will see why I am showing you this. So after substituting the Madelung equations, you get these two complex equations, and then you have to equate real part with real part, imaginary part with imaginary part, and these 2 equations basically yield 4 equations, 4 real equations that involve the angle theta and phi in the Bloch sphere with with the magnetic fields in each direction, in direction Z, Y, X, and so on, right? And then these four equations can be combined into just two equations, okay? So I showed you this because, as you can see, even though there are many equations, we haven't do a great mathematical job. It's just substituting, rearranging, and equating, right? So up to this point, mathematically speaking, it is not difficult using the Madelung picture. And we already get the two dynamical equations of the quantum bit. So in this case, remember that theta is related to the probability and phi is related to the phase. So here we have how the probability of the quantum bit is related to the phase and to the external agent, which is the magnetic field. And here you have basically the dynamics of the phase in terms of the probability and the magnetic field in the Z direction. So it's the spin analog of the hydrodynamic equations in position space. And as you can see, it is nonlinear due to the presence of the sine and the cosine. And it looks really complicated, right? But usually what in physics, what physicists do is the following. They say, I have a magnetic coil that will produce this magnetic field, and I want to know what is the quantum state, what is the probability, the output probability, right? So in this viewpoint, this is given, and the unknown is phi and theta. But when you go and you want to perform a quantum gate, when you want to work with the hardware of the quantum computer, the question is the other way around. The question is, for instance, let's say that I want to perform a quantum algorithm. I have my Bloch sphere, and basically I need this trajectory, this given trajectory. Then my question is, what do I have to do to the hardware so that I get this trajectory? So you see, it's the other problem. So in this hardware design, phi and theta are known, and the unknowns are precisely the required magnetic fields. So in this viewpoint, these two equations are extremely simple. Why? Because in the previous processor that I showed you, there are just two magnetic fields. One magnetic field in Z direction and one magnetic field in X direction. So there is no Y, right? If there is no Y, then this term cancels. And then, since what we want to know is the magnetic field, then we can just isolate this term by multiplying here, and in this case, dividing. And then we already have the required magnetic fields in terms of the given trajectory. So if I need a trajectory, then I just have to write down the functions of theta and phi. I put in these two functions, and then I will just calculate the magnetic field in the X and Z direction that will ensure these trajectories. So in this case, it is a very simple way of finding the required electromagnetic radiation to perform this quantum gate, right? And this is done from the Madelung picture. Because in the conventional picture, it is not that obvious. It is possible, but it's not that quick, so to say. And here, as you can see, we just computed the Madelung quantities, we substitute, we decoupled, we equate real part, imaginary part, then we combined, and we have this. So mathematically, it's very simple. And then with this in mind, for instance, let's say that I want to perform this quantum gate that takes the initial quantum state from here to this final state here in this way. Why? Because maybe that's what I need for my quantum algorithm. Okay. And then to perform this quantum gate, first we need to write down the trajectory, and basically to go from here to here in this way, theta is just this function and phi is this other function. Then we take this time dependency of theta and phi, we plug them in the previous equations, then we click, so to say, in plot, and then we already have the required magnetic fields Bx and Bz. And then we can go to the lab and then we can say, okay, I need some coils that will produce these specific magnetic fields so that I can, so that my quantum bit will follow this specific trajectory. Now you can say, but this looks like there is a divergence. But no, because remember that a quantum gate goes from one point to another point on the Bloch sphere in a given time, right? So here, for instance, there are 10 units of time. So that means that after 10 units of time, the coil and the solenoid will turn off. Okay, so there is no divergence. Now, another famous gate is the Hadamard gate. So you have the Hadamard gate does the following. It takes the quantum bit 0, and then it takes it to the equator. Remember that the Bloch sphere is a ruler of probability, and if you are in the middle, then that means 50% 0, 50% 1. And the equator is the middle. So basically, the Hadamard gate, basically what the Hadamard gate does is taking 100% quantum bit 0 to a 50% quantum bit 0 and 50% quantum bit 1. This is especially useful for a random number generator. For instance, when you want a random number generator, you apply a Hadamard gate, and then at the end of the operation, you have 50% of the time 0, 50% of the time 1. So when you perform a trial, that 0 or that 1 in the output is basically equally likely, and that's what you want in a quantum random number generator. And given this trajectory, if you take the functions theta and phi and then you plug in the previous two equations from the Madelung picture, then you get the magnetic field in the x direction, which is the common result, right? But in this case, we arrived from the other way of the problem. We started from a given trajectory in order to find the required magnetic field, and that's basically this is an illustration of how to use the Madelung picture, this hydrodynamic formulation, not in the position space, which is usually done in the literature, but working directly in the spin space. So as a little conclusion, quantum bits or qubits are a system with two possible experimental events. Energy is 0, E1, with corresponding probabilities, right? P0, P1, and these probabilities are precisely what the quantum gates manipulates. They manipulate the probabilities, not the energies. Okay. Okay, so the quantum gates in a quantum computer manipulate experimental preparation, which is probabilities, the phase, etc. And given the behavior of the probabilities, so the trajectory, the Madelung picture can be useful to design electromagnetic signals for a quantum gate in a simple way. Now that doesn't mean that Madelung picture will replace the conventional formalism, because the conventional formalism works very well. It already works very well since 3, 4, 5 decades, so that's out of question. But here the point is wondering in what case the Madelung picture can be useful, and this is a small situation, a particular situation in which Madelung picture can be rather useful and not time consuming to design the hardware of the quantum gate. So, σας ευχαριστώ για την προσοχή σας. So thank you very much for your attention.
So Moise, thank you very much. Do we have any questions from the audience? Okay, Professor Bud.
Hello, Moise Bonilla-Licea. First of all, there are other members in your family that are authors of the paper. I saw in one of your references 2 Moise Bonilla-Licea names, no? Licea M.
Yes.
And
Yes,
all the family, huh?
Yeah, it's family research,
yeah.
So to say. Yes.
I will. Yes, I liked your talk. Yes, very much. It is very clear, very pedagogical, and I will send you my email. If you could please send me a PDF file of your transparencies.
Yes. I would be glad to send you the slides. Yes.
Yes, but you today you had time, I guess, to provide only the framework within which quantum mechanics can be studied, but you didn't go into any of the specific computation of dynamics in particular examples of how do the quantum mechanics work for a computer. I had the idea that was quite theoretical, but in practice, where are we today in terms of implementing?
Okay.
The Madelung picture, I understand, is rather new or recent or different than what one hears often.
Okay, so let's go by parts in the question. First, Madelung picture is just the name of the hydrodynamical formalism.
Hydrodynamical approach.
Mechanics, yes. It is also known as the Bohmian mechanics, right? From the works of Bohm. Here we use the term Madelung equations because Madelung picture, because Madelung found it first in history, so 1926.
So that's equivalent to Bohmian mechanics.
It's Bohmian mechanics, but without extra postulates. It's just a hydrodynamic
that's what you call extra postulate.
Can you hear me?
Yes. I expect Thanasis will have something to say about
we have
Bohmian mechanics.
Now, Moise, can you hear me?
Yes.
I think the problem is okay now.
Can you hear?
It was frozen. The screen was frozen for several seconds, but now, as I can see, it is okay.
Is everything okay?
Yes, unfortunately, we had a technical problem early in the morning, so I hope this not disturb again your talk. Okay. Continue. Please continue. Yeah, it says my interconnection is a little bit unstable.
Okay. Okay.
Everything's fine.
Okay, thank you very much. So the second part of the question is where are we? So this might seem a little bit like theoretical, so to say, but for instance, I will show you what we have in the automatic department of the Simba staff. Maybe that will so this. So for instance, we have in the department of automatic control at Simba staff a quantum processor from 1 qubit. Actually, quantum processors, you can buy them already in the market, so to say. It's not so science fiction. So that NMR processor that I described, this is how it looks like. So there is like a big solenoid, and then inside this solenoid there is a coil around a reservoir of water, and then there are some electronics here where you can manipulate the duration of the magnetic pulses. And then here in an oscilloscope, you can register the behavior of the components of Sx, Sy, Sz. So basically, where are we today? Nowadays, it is possible to buy quantum processors of 1 qubit, or for instance, this other one we have in the department of automatic control, it's for 2 qubits. There are two, instead of a solenoid, you have two permanent magnets of 0.6 Teslas. So it's very strong, very strong magnet. And then you have a test tube with either water or dimethyl phosphate or some chemical substances that have a given nuclei, and in these nuclei you manipulate the spin. So the NMR processors are usually the most common in the market, because they are as far as I know, they are the only ones that work at room temperature. There is no need of of cryogenic systems or vacuum systems. It's just two magnets and a test tube. And then you can replicate all the quantum algorithms with 2 qubits or 3 qubits and read the signals and take out the probabilities. And these two systems, we have them in the automatic control department at CIMSTAF. So it's not science fiction, so to say.
Yeah, you can use this as an actual computer to make computation.
Yes. So basically, well, here maybe it is not well seen, but there are the quantum gates in this. So you can perform the quantum gates by applying the default electromagnetic pulses, and then you can retrieve the probabilities, and the probabilities are basically the outcome of the algorithms. So yes, you can. Sorry, you can perform quantum algorithms with this or this. Yes.
And suppose you wanted to solve a problem of, let's say, a zero solution or equilibrium state of a large system with a lot of particles. Simply solving a set of nonlinear algebraic equations, let's say.
Okay.
To try to find. Can you test that on your computer?
Okay. So in order to know how to solve that problem, maybe it's important to go back here. So for instance, this is a paper basically that reports how to apply quantum computing to particle physics. So for instance, if you have a problem, the first step that you need to do in order to apply a quantum algorithm is translate this problem into a search problem, right? So you have to somehow translate every event into a binary register, right? So for instance, here you have some registers. Every register has a meaning. Maybe this meaning maybe this register means that there was some particle collision. This other register means that there was some kind of reaction, etc. Then you have like millions of possible events. You have a large database, and you are interested in a given event, and you don't know if that event occurred or not. So basically, what you need to do is you can program.
Search.
Yes, exactly. You need to search. Then you need to do a search, and to do this search, quantum computers are very good at it, because you can program this search with electromagnetic pulses, which are the programming is already available. Let me show you. Well, once you program, you run the algorithm, let's say 1,000 times, 2,000 times, and then you will get a probability peak. And this probability peak will occur in the register that you are interested in. So you already found the event, right? Just by repeating over and over again the same algorithm. And regarding the feasibility of the, the feasibility of the programming, we have indeed in the Department of Automatic Control the processors for 1 and 2 qubits. But if you need like more qubits, what is custom to do is to go to one of the services, the cloud services that are provided by several companies, Microsoft, Google, IBM, etc. And that
I understand. I understand. Very good. And my last, I'm monopolizing the discussion for a moment, but the last question I would like to ask. You said the Madelung picture is somehow analogous to Bohmian mechanics, but I didn't see any momenta or any position variables, Hamiltonians and so on. How does that? Maybe Thanasis will comment on that later.
Okay, so that's a good question. In one of the, where are you? Give me a second. Here. So basically, where does it stand? So what is Madelung or Bohmian, the formalism? Because many have the idea that it's just the position and momentum space, but actually this hydrodynamic formulation is not dependent on the representation. It's not dependent on position representation or momentum representation. It's just a hydrodynamic formulation in any representation. And here there are the 3 formalisms. So I show them because it's interesting to understand the place of Madelung. So basically, in a nutshell, Schrödinger basically says the quantum state behaves in an ondulatory way. So the dynamical equation related has to do with a wave equation. And that's the object that carries the probabilities. That's it. Heisenberg, what does Heisenberg does? That the observables are ruled by dynamical equations that are characteristic of particles in classical mechanics, no? And then what does Madelung picture says? That the observables are objects that are ruled by hydrodynamic equations, transport equations. For instance, yes, so for instance, the normalization, if you substitute f by 1, you have the derivative of rho, 1, the derivative of 1 is 0, this will be 0, and then this is 1. This imaginary part will cancel the imaginary part of the Bohmian the Madelung momentum, and then you will have the real part, which is just the nabla of phi. And then you recover the continuity equation, derivative of rho plus derivative of x, derivative in x of rho times nabla phi over m equals 0. So, and if you substitute x or p, etc., then you get the transport equations of in position space, momentum space, etc. But
like
yes,
hydrodynamics, huh?
exactly. It's just a representation. It's just how to deal with the dynamical behavior of the system.
Right. Very good. Very interesting.
So,
Anyone else?
Moise, I would like to congratulate you for your interesting talk. We are very glad that we find
very pedagogical. Very
Yes.
pedagogical.
From my point of view, I see a way to implement Bohmian quantum mechanics. Here in our center, we are doing the dynamics with Professor Kondopoulos. We are working on Bohmian quantum chaos. So we are always trying to make a comparison between the classical Hamiltonian chaos and Bohmian quantum chaos, which is a fundamental theoretical question up to now. Okay? But here you gave us a totally different point of view. Yes, for our theory. I would like to make some comments, nothing more. No, I have no questions. Actually, I have thousands of questions, but okay. The problem with qubits, the quantum bit systems, is what are the physical realizations of them? What are going to be the realistic physical systems that are going to play the role of qubits? And now Moise automatically changes his pages to show us the different candidates. The problem in quantum computing, the most difficult, as far as I know, is the problem of decoherence. Decoherence is a fundamental process occurring in quantum systems during their very fragile character. A quantum system is always connected to its environment. So you have a qubit, say a spin qubit. Okay, what is a qubit? A qubit is a quantum system that can be found in two very distinctive states called 0 and 1. Okay, and in all the intermediate superpositions. Okay, these states 0 and 1, as Moise said us before, they have to be reachable from 0 to 1 to go through a path, and this path is going to be implemented by a set of unitary transformations. Okay, that is why you have the reverse process, and this computation is reversible. Excuse me? Okay, but in practice, all the computations, if we want to be 100% accurate, they cannot be totally reversible, okay? Due to the leakage of dissipation and information between the system and its environment. That is why, as Moise told us before, the center of the research center of Mexico, where he conveys his research, has to do with you have only NMR.
Yes, in this at Simba staff.
I would like to ask you if you have problems related to the openness of the system. The problem of decoherence.
Yes.
That is why in the old books of quantum information theory, whenever there were always the mathematical introduction of qubit with the Bloch sphere, okay, which corresponds to all the possible state vectors in the Hilbert space, the pure states. But in practice, due to decoherence, you are always led to mixed states, which are inside the Bloch sphere and not only on the area. So, do you find any problems? Can you fight decoherence with your system? Do you have any inaccuracies due to decoherence? Because quantum mechanics, and I'm stopping here because quantum mechanics has already been passed to open quantum mechanics. I want to remind you the book from Sanz, Alvarez, Oriols,
Yes.
Open Bohmian quantum systems. And actually, this is one of our future plans here in order to examine chaos in open quantum systems. Okay.
Okay, let's hear the answer.
You can tell us something about that, and we are done.
Yes, so you are right. The coherence is a very important problem. Actually, a lot of research around the Lindblad equation and
Exactly.
this,
The little master equation.
yes, the master equation, etc. So basically, well, in this case, the processor is well designed because the timing of the pulses are shorter than the coherence time. So you can perform the gates before you lose the state. Actually, if you can see here, well, maybe it's not very clear, but there is a decay. So this is already the decay due to the decoherence. So what is studied is the oscillatory part, which is right before the decaying, right? So experimentally, you send the pulses and your quantum gates, your pulse needs to be in time, it has to be shorter than the decoherence time. So you have to first analyze and then determine what is the coherent, the decaying time. And then you have to do the design the quantum gates shorter than that. And then when you perform the calculations, the signal of decaying will always occur because, as you said, quantum systems are inevitably in an environment. So this cannot be unavoided. But what is done is that your pulses are shorter, so you only have to take the Fourier transform to analyze the frequencies of the part without the decaying, so to say. So there is no problem on the decoherence. In this kind of in this kind of setups, it's not a problem as far as you take it into account, so to say.
Okay. Thank you very much.
Good.
One question.
Good question. You said that you repeat the calculation many times to get the probability. Is that correct?
Yes.
If that is so, then doesn't that negate the increase of quantum computing?
Can you repeat the question? Sorry, I didn't hear.
Μπορείτε να το πείτε το μόνο το τελευταίο κομμάτι.
You repeat the calculation thousands of times, then your speed, your calculation speed is down by 1,000 times. So
okay. So for instance, well, first, how does it look like, no? So for instance, you program in Python, let's say you want a quantum random number generator, right? So you go to IBM, then you declare in Python all the respective libraries. You create a register of 1 qubit, and then you apply the Adamar gate. You measure, and then you run the well, here I run it for one shot, but let's say you run it for 1,000 trials, 100,000 trials. So in every trial, in the program, basically will retrieve if it was a 0 or a 1, and then it will construct the histogram, right? So by necessity, you need to repeat the algorithm a large enough number of times because you need to make sure that you are handling the probabilities that you want. So for instance, here after 100,000 trials, basically we can see that we have 50-50, a qubit of 50-50, okay? So by necessity, you need to. Now the question if it will slow down, yes and no, because for instance, imagine you want, you need 1,000 times for repeating this algorithm, but this 100,000 times, etc., is the same number of trials for 1 qubit, 2 qubits, 3 qubits, 4 qubits. So you can extend your database, and it will always be more or less be the same amount of trials, right? And even though it seems a little bit excessive, it is not, because the time of the time for performing a quantum gate is very short. Well, it depends on the processor, but it can be microseconds or nanoseconds. So it says, yes, it's 1,000 times. Okay, it's 1,000 times microseconds. That's 1 millisecond. And definitely 1 millisecond is shorter than 1 month, for instance.
So the rate is...
Yes, but if the outcome is only 0 and 1, you do 100,000 trials to get the probability. If the outcome is a very large number of outcomes, like numbers, the results of the calculation, then the number of trials to get the probability at all the possibilities will be much higher than 100,000. So the more complex the calculation, the more trials you do, the slower the outcome.
Okay.
Doing quantum calculation instead of a standard calculation.
Okay, that's a very interesting question. So we have to distinguish between two types of computations. There is the arithmetic computation. The arithmetic computation is very good in classical computers. That's a fact. For search problems, on the other hand, quantum computer, even though you need to repeat 100,000 times or the required amount of times the algorithm, that is still shorter in time than using a classical computer for a large database, so to say. So if you have a large database, yes, it makes sense using quantum computing. But if your database is small, then no, you can use classical computing. That's faster, right? So it really depends on the problem that you are looking at and the size of the database.
On the contrary, if the number of outcomes is millions, for example, and you want to fill all of these million outcomes with a probability, you will have to repeat the experiment hundreds of thousands of millions to get the probability. The larger the outcome, the larger the number of trials. But okay.
In this case, it is important that let me see. So when you have when you perform the quantum algorithm and you have, let's say, four outcomes. Let's say you have 4 outcomes. Then you need 2 qubits. Your database is 4 data. Then you need 2 qubits. You have 2 qubits, and then you have to send the electromagnetic radiation. But it doesn't matter if it's 1, 2, 3, or 4. Because the whole system in quantum in the quantum system, all the qubits are in a tensor product, so to say. So they are a whole unit, so to say. They constitute a whole unit. So when you start sending when you start sending the electromagnetic radiation, etc., even though there are more qubits in your database, it is still short in time with respect to the classical case for a large database. It's so basically the use of when to use quantum computing, I would say, if you have a large enough number of data, then go for quantum computing. And actually, the number of qubits is not very large because, for instance, 2 data, 1 qubit, 4 data, 2 qubits, 8 data, 3 qubits. and so on and so forth. 20 qubits, then you have, I think, 1 million of data. You see, so it's not the amount of qubits, usually it's not large. So with 20 qubits, you can do, let's say, 1 million data.
Okay.
So, yeah.
So Moise, thank you very much. Again, congratulations.
Thank you very much.
As regards your talk, it is recorded. It has already been recorded, and it's going to be uploaded in the YouTube channel of the Academy of Athens. I will upload it today or tomorrow, and I will send you the link in order to share it with your friends and colleagues. Okay?
Thank you very much.
Yes, and of course, and
bye, guys.
The web page as well. I will send it as well. Okay. Thank you very much. Bye bye.
Okay. Thank you. Bye bye.